meeting is being recorded.
Okay, so hello everyone. So welcome to our this week Rutgers Efficient AI Seminar Talk. And today we're very glad to have the Dr. Tom Senjong, and he also graduated from our Rutgers ECE department before to give us this talk towards a benchmark for automotive computing. And Tom is currently a senior software engineer at Cruise, where he serves as a technical lead for the compute platform groups. He also served as the chair of the MLPerf Automotive Advisory Board. Prior to his current role, he led the distributed machine learning platform optimization efforts with Tesla and served as the director of the AI Co-Design Center at Wave Computing. His research primarily focused on the intersection of parallel programming models and the computer architecture design, and the impact that this has on machine learning workloads. He completes his master and PhD degree from the University of Delaware and a bachelor degree at Rutgers. Okay, so now let's welcome Tom to give us this talk.
All right, thanks, Bo. So today I'm going to be talking about the work that we've been doing in ML Commons to develop an AV machine learning benchmark. So first we'll do a quick intro to what ML Commons and MLPerf are, and then we'll dive more deeply into the work that we're doing in the automotive space. So first of all, so what is MLPerf? So it's a collection of machine learning benchmark suites supported by a nonprofit group that we've since created called ML Commons. This has grown from the original group of 20 people when we started to now we have over 70 participating organizations with over 1,000 researchers and engineers. We have benchmark suites for both training and inference, as well as domain-specific benchmark suites like MLPerf HPC, MLPerf Mobile, etc. So major goals here are we want to enforce replicability for reliable results. We want to make sure that the workloads that are in these suites are actually representative of what's being used in industry. We're trying to drive innovation to improve the state of the art for ML. And we want to accelerate progress in really a fair and useful measurement rather than people kind of being at the mercy of the marketing departments for the very large AI companies.
Hello, Tom. Sorry to interrupt you. It looks like right now I cannot see your screen. So I'm not sure whether for other audience, can you see Tom's?
Yeah, it looks like it did stop sharing. So let me.
Okay, yeah, and I can see that.
Okay. Yeah, so back where we are. So we're looking to focus on both commercial and research communities, and we also want to keep this affordable. So this shouldn't only be for the big guys like Google, NVIDIA, et cetera. So as you mentioned, this is a global organization. We have you can see some of our members here, which is basically a who's who of the field. And we also have academic researchers from some of the top universities in the world, including like Harvard, Stanford, Berkeley, University of Toronto, and some others. The stated goal of ML Commons is to accelerate the machine learning innovation to benefit everyone by looking at trying to build out the entire ML ecosystem. So the main three pillars are benchmarking, data sets, and best practices. Today, we're primarily going to focus on the benchmarking side of things, though. Just a quick glance at the org structure here. So we've got quite a few different working groups now, in addition to the main inference training and data sets and best practices. Off to the side, you can see research, which is where this work currently falls. And with the overall goal of this being sort of better ML for everyone. So ecosystem improvements drive progress for more capable, less expensive ML. And I guess the key question here is, so first of all, why benchmark ML systems? So if you look at the first figure here, you see all the different components involved in the stack. And if you do like a cross product of all of them, you come up with many, many different configurations. And in order to result in an efficient system, you need all of these components working together seamlessly. And given the exponential growth in research in this area, you really need something uniform that can level the playing field. So prior to this, you have the state of ML benchmarking, where let's say you're comparing two systems. Questions are, okay, what task are they doing? And if they're doing the same task, what model, what data set, batch size, quantization techniques, software libraries. And unless some of these, you can enforce conformity among some of these things, you're really, you're comparing two different things and there's not many conclusions you can actually draw. So now we'll talk a bit about the training benchmark specifically. So the benchmark definition really is just, we have a data set, we specify a model, and we specify a target quality. Specifically, we have two divisions here, closed and open. In the closed division, we specify the model that has to be used. This allows for direct comparisons. And in the open division, you can use any model. So let's say, sticking with the image classification, if you come up with some new model that's 10x faster than ResNet 50, you could then submit those results into open and show off the performance gains from the innovative work you've done. Looking at the MLPerf v 1.0, which is a few months old at this point, we have these following training workloads. So we're looking in domains such as image classification, which I mentioned, image segmentation in the medical domain. We have two object detection benchmarks, speech recognition, NLP, recommendation, and reinforcement learning. So we're trying to capture as many of the key markets as we can here. The main metric that we're looking at is time to train. Previously, a lot of people were looking at capturing throughput, which is fairly easy and inexpensive to measure. However, there's a lot of tricks you can use to increase throughput, which will increase your overall time to train. For example, if you just arbitrarily lower your precision or just infinitely scale your batch size, you can get great throughput that way, but you're going to end up training for more epochs to reach convergence, if you even can reach the target convergence at all. So that's reporting those numbers can be a bit misleading. So we went with time to train. The drawbacks of that are that doing a full training run can be computationally expensive and there can be high variance there, but it does seem to be the least bad choice available. We've made a point to explicitly exclude a few items for the sake of fairness. So like system initialization is highly dependent on your cluster configuration and state. Model initialization, which for big systems can be high overhead. And if you have a small benchmarking data set, that initialization could be the dominant factor, obscuring the information we really want. And also data reformatting, given that if we gave a very specific data format, that could give advantages to certain vendors over others. The major challenges you face with an ML training benchmark is, as we mentioned, very diverse software stacks and hardware systems. So you generally can't use the same executables, and in many cases, you can't even use the same code. If you have different training on larger scale systems or using different numerics requires tuning. So if you're scaling out on a cluster, you then would need, assuming you're sticking with data parallel approach, you would need larger mini batches. So you need different optimizer hyperparameters, and hyperparameter tuning is very expensive. So that can be unfair, which is why people have to publicly disclose their hyperparameter settings, and other vendors can try to basically borrow those to see if if that improves their model, since the focus is that we don't want this to just be a hyperparameter tuning competition. Another main big issue is convergence can be stochastic. So you have random weight initialization, non-deterministic floating point effects. So that's something else that has to be considered. Just looking at two cases for the convergence variance, we see In the case of ResNet 50, it actually does, we don't see a lot of variance here. It looks fairly stable. However, for the reinforcement learning benchmark, Minigo, you can see just using 5 different seeds, the number of epochs you need to train to the specified quality level can vary by quite a bit, between like 75% to 100% in some extreme cases. So, sort of talking about how we've addressed this, the issue of diversity in the software and hardware, we've provided reference implementations that people can use. And given that many vendors do want to re-implement things, we have specific rules for how you're allowed to do that. Dealing with the issue with hyperparameters, we've limited the tunable ones, and then by supporting the hyperparameter borrowing scheme that I mentioned, this we try to enforce fairness here. And then for the stochastic convergence, we deal with that by requiring multiple runs. And then we use what's basically the same scoring system they use in the Olympics, where you drop the lowest score, highest score, and then you average the remaining 3. So talking about the purpose of good benchmarks. So we have, we've got defined set of problems. We have clear metrics. Competing engineering teams try different approaches, and you have objective results showing what works best. And as people understand the performance, and this allows for better like hardware and software optimizations. And so quoting Dave Patterson, for better or worse, benchmarks shape a field. So this is an area you really need to get right. So looking at the first 3 rounds we've submitted, we're showing, you can see for 5 of the different benchmarks, the relative speed up you're seeing. So it's pretty clear that this is actually driving industry progress quite significantly. In particularly, in going between version 0.5 and 0.6, people are actually running on the same hardware platform. So that performance gain actually comes entirely from improvements in the software stack that were driven by understanding where the performance bottlenecks were. Next, we'll talk about the inference side of things. So also looking, this is a few months old, but looking back at version 1.0, we have overlap with the training benchmarks where necessary, but there's a few that are specific to the inference side, notably like SSD MobileNet. Given that inference tends to have a much more diverse range of use cases, we have multiple scenarios here that can be considered. First is single stream, where you have images coming in, let's say on a cell phone, and then you process them as they come in. Another is multiple stream, where this would look more like something you see in like an autonomous vehicle, where you would have multiple cameras or LiDAR sensors and the like, and you have to be able to process all of the samples coming in concurrently. Next would be the server case, where you have inputs coming in based on a random distribution, and you have to handle them as they come in. Finally, you have offline, where you just basically have a batch of inputs and you want to process them, and you don't have like a hard deadline, so that's more throughput focused. Talking about the different metrics, so for single stream, with single stream, you have just a set of inputs coming in one at a time. So what you really care about there is latency. For multiple stream, what you're trying to do is you scale the number of inputs that you can have to the point where you can still satisfy your latency bound. So the reported metric would be the max number of streams that you can handle. In the server, what you're reporting is max queries per second, subject to the latency bound. And for the offline metric, it's really just a pure throughput. On the implementation side, you see in inference, you see an even greater range of software and hardware solutions than you do in training. So we allow the submitters to re-implement the model subject to some inference rules. So we have, like in the figure here, we have a system under test. We provide the weights from the trained model, and we use the load. We have a load generator we built to feed inputs into the system. It times them and then validates the outputs. We have, as I mentioned, we have pre-trained weights for the closed division. We'll talk a little bit about that later. So one of the big things is on the inference side, quantization is really important for performance, but this is not intended to be a quantization contest. So people submitting to the closed divisions, they are allowed to quantize, but there has to be like an underlying principle methodology to it, and they have to be able to describe it in such a way that's reproducible. They are allowed to calibrate their data on the quantized set, but they have to use this fixed set of data. They're not allowed to retrain though, given that this isn't a retraining contest, but we do provide 8-bit models for people. Now having gone through a broad overview, we'll dive into the AV side of things, which is the work that we're doing currently. So first of all, as you've seen in the previous figures, MLPerf currently doesn't have a representative AV benchmark. And given that in the next 4 or 5 years, this market is expected to exceed over $500 billion, that's something we want to address. So we need to develop a benchmark which can guide hardware, software, co-design, and selection in this domain during the benchmark's expected 2-year lifespan. So the first question is, out of all the workloads running in the vehicle, we need to choose one particular task. This needs to be representative of ML workloads for autonomous driving. And we want it to be a computationally expensive portion of the stack, since that's something that we wanted to address a key issue that vendors will face. So as I mentioned, there's many different tasks to choose from. And first of all, we're doing machine learning benchmarks. So we specifically want this to be a machine learning focused benchmark. So many tasks like mapping and localization or path planning currently have solutions that don't utilize ML. So some people are moving in that direction, but it's not necessarily the standard yet. And given that most perception tasks are now done using neural nets, we've decided that domain is most suitable for this. To help us reach consensus on this, we've put together the Automotive Advisory Board, which is a team of experts in this domain who can provide insight regarding what would be useful to them. So this is made up of people who represent companies who are basically consumers of AV compute rather than producers. So you won't see people from like NVIDIA or Intel on this board. Current members, we have people representing Waymo, Zoox, Cruise, Toyota Research, TuSimple, as well as professors from the University of Tokyo and Tsinghua. We also previously had someone from Tesla on the board, who people probably recognize that name. So based on the input we've gotten from the advisory board, we've settled on 3D object detection as the workload of interest. So this is generating bounding boxes on objects, so cars, pedestrians, cyclists. This is clearly relevant to the AV industry. And other areas like 3D tracking do utilize detection. So this is useful in other areas of the stack as well. And then considering why 3D is that we want tasks that are relatively compute intensive. And additionally, most 3D models actually do use 2D models in some cases. So for example, if you look at the structure of the point pillars network here, you notice they are using a 2D CNN backbone, even though this network is intended for 3D object detection. Next, we'll talk about data set selection. So based on the feedback we got from the advisory board, we want the benchmark to accept inputs from both camera and LiDAR sensors. Additionally, we want some diversity with geography and lighting, and we want to make sure that there's quality ground truth labeling provided. So we've come to decide we're going to be using Waymo's open data set. So they have this was generated from data collected in multiple cities, so both San Francisco and Phoenix. It's run during various times of day with various weather conditions, so there's diversity in terms of like visibility. It does have both camera and LiDAR and ground truth, and the labeling is done very well. One of the more interesting things we've seen when doing this is that if you train on Phoenix data, test on San Francisco data, it actually performs quite poorly, suggesting that there is a domain gap between the suburbs and city driving. So having a data set that captures both of those domains is quite useful. Just comparing some metrics from Waymo versus some other prominent data sets like Kitty, New Scenes, and Argo. So with Waymo's data set, it has more scenes and more hours of footage. There's more objects, multiple LiDAR sensors, and it also covers a much wider geographic area. So now I'll talk a bit about 3D object detection models. So typically, you see, first of all, LiDAR-only models outperform camera-only models. This is based on data we found on the New Scenes leaderboard. And in 2021, the top fusion methods actually were only slightly better than LiDAR-only methods. So this indicated there was a gap in research with fusing camera and LiDAR features. However, that is beginning to close now. Just a few basic points about LiDAR models is, so first of all, they're an unordered set. So the model needs to be independent of the order of points processed. So we have symmetric functions here to be invariant of the point permutation. So point net is an example of that here. Additionally, you typically, because you have a large number of sparse points, many networks leverage point grouping, where you kind of generate a voxel grid in space. So this works for 3D convolution. You can also do point grouping in 2D approaches as well. There are some models that avoid this step and operate directly on the points, like point RCNN, but that's more of the exception than the rule. And then also you're going to have a detection head like most object detection models. So typically you make use of 2D detection or similar methods, or in VoxelNet here, it makes use of, like I said, doing heavy 2D convolutions like other detectors. So this is just summarizing the points that I covered previously. Where LiDAR has issues is that, first of all, LiDAR points are sparse. So the density of the points is proportional to the distance from the source. So objects that are either smaller or farther away, you may not get enough data points to really capture what's you're seeing. So generally, like images are better for detecting small objects since you have dense pixels available. So considering LiDAR and camera fusion, so there are multiple stages where this can be done. The common approach is you take features and combine them. You get these from Backbone for LiDAR or the camera model, and then there are multiple places where you can combine these features. One commonality among all of them is the use of backbone models. For example, you can use ResNet as for the image side of things. Just looking at, let's say, the cross-modality 3D object detection model here, you can see you have your camera, your image backbone network, your LiDAR backbone network, and then it starts fusing things to do proposal generation, and then also finally the feature fusion prior to the final detector. Other approaches, you can actually fuse different approaches from the same sensor modality. So for example, in MV3D, they have a backbone to do LiDAR with bird's eye view, LiDAR with front view, and then also camera. And then they're fusing all three of these together. Next, we'll talk about the baseline model that we've settled on based on the advisory board's feedback. So first of all, we'll talk about requirements. So it needs low latency during inference. It needs high accuracy for the because this is a safety critical system. We want the model to be relevant to industry. And because of that, it should be a relatively recent model, but not the latest thing that you've seen. So like models from CVPR this year will not be deployed in vehicles right now, given that there's a fairly lengthy validation process there. And we want to make sure that it does use both camera and LiDAR. So comparing a few models available, there's a few that we talked about previously, also point painting and some others. Comparison here based on just this data is fairly difficult, given that like not everyone is reporting inference time. They're run across different data sets and so on. As I mentioned, it's also hard to compare results because in many cases, these results we've seen, they're published in papers. However, if you actually look at the leaderboard for the data sets they're claiming, they make no appearance there. So it's hard to verify the accuracy of what they're claiming. So we've settled on point painting as a baseline model. So it has good latency at its time. So this was published 2 years ago. So it's no longer state of the art, but it was very good at that point. And it was one of the first models to actually show accuracy gain from fusing both LiDAR and image data. And since then, others have actually used point painting techniques to improve their models. So Centerpoint would be one example of this. You can see people have managed to use these techniques to improve actually quite a few models here. So the basic idea behind point painting is you take a LiDAR only model and you add semantic segmentation. So you perform segmentation on your camera images, you append the segmentation output to the LiDAR points, and then you use use the LiDAR only model with the addition of this segmentation data to generate your output bounding boxes. Just a quick overview of semantic segmentation. So given, in this case, you take an image as your input, and each pixel is then labeled with a class. So that could be car, road, pedestrian, makes, like most image tasks, it uses convolution pretty heavily. And it's also useful for other AV tasks like lane detection, road segmentation, and the like. So painting the LiDAR points with this data basically is just appending the classification scores from the segmentation model to each LiDAR point. So if you have a LiDAR point with X, Y, Z, and you have 3 scores coming from the segmentation model, you now have a tuple with 6 elements, and you would update your LiDAR model to accept the larger input dimension. So architecture requirements for handling this model. So we major things here are you're going to need to be able to handle fast convolutions, given that that's going to be the bulk of your compute. We also have point aggregation layers that need to be handled. So typically those are fully connected layers along with max pooling. Finally, next steps for this are, we're in the process of doing implementation now. So determining some of the details of it, accuracy metrics, getting this working with our selected data set, fixing hyperparameters for the reasons I mentioned before about we don't want companies that have money to do large hyperparameter searches to win by default here. First, given that point painting is a fairly generic approach, there are questions about what model components we should use. So we've, based on the feedback we've gotten, using Deep Lab for the semantic segmentation model and point pillars for the LiDAR model, it seems to have been the choices that the advisory board members gave. If in the future this needs to be adjusted, we can do it given the modularity of point painting, which is one of the nice things about it. Finally, I just want to give some acknowledgements to collaborators on this. So Rod Shoje is a PhD student at UC Davis who's doing a lot of the implementation of the reference models. John Owens is his PhD advisor, and then Pinar Milian Oshilek at Sac State is also one of the collaborators on this. And we've also had many contributions from other ML Commons members, so I don't want to ignore them either. Additionally, if anyone is actually interested in getting involved with either ML Commons broadly or specifically with the A/B benchmarking effort, you can follow this link and it has instructions for how to get involved with us.
Okay, thank you, Tom. Thank you very much for this very interesting talk to let us know the current state of art and the progress in the automotive computing, the ML Commons. So some questions from the audience. You can unmute yourself or to input your questions in the chat box.
I have a question for Tom.
Yeah.
Tom, this is Larry O'Gorman at Bell Labs. One of your earlier slides in this talk had a bar chart of the substantial improvements you guys have done, well, MLPerf has done in efficiency for different, I think you had vision and other things. So this question might be, that's the slide, thank you. This question might be unfair because I refer back to something that I've actually quoted a number of times. I wonder if it's true or not. There was an article written, I think it's published in Archive, it was by Thompson, Greenwald, Lee, and Mansell, called Computational Limits of Deep Learning. And it was subsequently referenced in New York Times and IEEE Spectrum. And it extrapolated training costs with of CO2 production for training, I think it was a vision task on ImageNet for down to 5% accuracy, and extrapolated that by I'm looking at the chart here. Well, I don't see it here easily, but in 2 or 3 years to train one of these models would take more CO2 than is created in New York City in 1 month. I don't know if you know this. If you do you have a comment on it?
Yeah, so I'm aware of this, and there are some of our collaborators, particularly at Meta, have been publishing papers about this. There's one, I think, at MLSys this year about carbon footprint for ML training. So that's very much an issue. From talking with people at hardware vendors, though, actually the carbon footprint from silicon production actually is still by far the dominant factor here. So this is an area that you really, in the sake of the carbon footprint, it really needs to be tackled from multiple areas. So there's a lot of work being done on like green data centers and the like, which is it's certainly a non-trivial improvement, but this is the lifetime of the chips operating CO2 is still significantly smaller than the cost of making it in the first place, especially at the latest process nodes.
It's very interesting. I wouldn't suspect that because these things are, I mean, in a car, I would think that they're basically recognizing at frame rate. So they're doing a GPU calculation. I know the GPUs that I use are sort of like a 100-watt bulb. I don't know if that's the same in a car engine, but you say that even for the millions of chips that are made, that the CO2 cost of production is higher than all those chips that are running in cars over the lifetime of the car.
Yeah. So also I think the carbon footprint of the chip, at least in the vehicle, is highly dependent on what the market for that vendor is. So, yeah, for example, companies like Waymo and Cruise, where the vehicle is supposed to be generating revenue around the clock, they can amortize the cost of a much more heavyweight compute solution, whereas like Tesla is selling personal vehicles, so they need something that's much more constrained, given that, first of all, a consumer is not going to pay for an extra 15 grand worth of compute hardware. And also range is very important, so you need something more energy efficient.
Yeah, great, thank you.
Other questions from the audience?
I can ask a smaller question than my previous question.
Go ahead.
And that is the benchmarking that you're doing. It's strictly algorithmic. I mean, I didn't understand that from the talk, because you do talk about hardware here as well, but it would be very difficult to benchmark hardware from a whole bunch of different automobile manufacturers, that it's used in all different automobile manufacturers. But of course, latency is an important thing. So how do you deal with the software and hardware interaction?
So this is something where we have some rules about software, basically, like particularly since I already have this slide up, the software stack is likely different for every vendor. This is one of the main challenges that we addressed. However, you have to specify what you've done, and we have to be able to verify that any changes you made are at least computationally equivalent. So we provide reference implementations using PyTorch and TensorFlow, particularly for image classification. NVIDIA likes to use MXNet, which is fine, as they can demonstrate the equivalence there. And then obviously they're running their own software stack. Intel's running something else. However, they're still running the same workload, and we have the submitters do have the opportunity to audit each other's submissions in order to make sure that everything's on the up and up there.
Right.
And we make people specify things like what software they're using and the like to make sure that these things are actually reproducible.
Yeah. Yeah. Good. Thank you.
Other questions from the audience? Actually, Tom, so I have some questions about the benchmark models and the data set and the task. And the first, so right now, so the models used in the automotive tracking, the MLPerf, that is, I think, is to fuse the LiDAR and the camera, right? Mm-hmm. And so how about that for some other fusion, like including the millimeter wave signal there? Mm-hmm.
So that's one direction you could go, but one of the questions we ask the advisory board members is what input or combination of inputs do you think would be most representative of what people do? And the consensus that we reached based on their input was camera plus LiDAR is what we should follow. So yeah, that's what you're asking is one of the open questions that we had when we started this, and that's being able to answer these questions from like a who's who in the field is one of the main points of why we created the advisory board.
Okay. And also another question that, so right now in your presentation, so the task you show us is the 3D object detection, right? And I remember in one of your slides you show that actually for the entire computing pipeline for the autonomous driving, there are actually several different computing stages and the tasks there. And so how about the current, the progress to decide the representative, the models for the other task, like for the planning and the control and so on?
Right, so that's a question where I think, each company has their own approach for this. So there are more traditional approaches to path planning. There are some companies that are looking at ML-based approaches and are migrating to that or have migrated, but not everybody is using ML for path planning, whereas for perception, pretty much everyone is using ML for that now, which is one of the reasons why we said, okay, that's where we're gonna start. Depending on how this evolves, there's a possibility for adding other models to this later, but for now, we decided to limit the scope to just a single model. And we decided that this would be the most important one to choose from.
And based on observation, actually, that is kind of right now, the computational cost at the perception one, that is kind of the right now the bottleneck for the entire pipeline.
Yeah, so doing all these very heavyweight convolutions is not cheap. And when we were selecting the domain task, the thing we asked the advisory board members is, what's the heaviest compute task that you have? And almost everyone said 3D object detection.
Okay. And also, actually, so it brings up my another question. So how about the transformer?
So some people are looking at that for future generations. I've only worked at 2 of the major companies, so I can't say what the rest of them are doing, but I think it's at least an area of exploration. As I mentioned, there's a significant lead time between when a model gets either developed / published and when it actually goes into production. So I think there are very few, if any, like visual transformers currently in use in vehicles on the road.
Okay, you mean that right now there's some kind of the gap between the industry and academia for the
right. So I think it's an area with a lot of promise. Before people actually put them in vehicles, there's quite a bit more work that still needs to be done regarding does it work consistently across inputs? How deterministic is your performance? Is your latency with this model and things like that?
Okay, I see. Thank you. And also, I was wondering, so like we know that like in the general ML so they have the training and the inference that have some like the edge HPC, right, and the mobile and some. And for this, for the specific automatic track for the MLPerf, so right now, so it's kind of a training or the inference be more focused?
So the plan is for this to be a benchmark for both training and inference.
Both training and the inference. Okay.
Yeah.
And I think there's a very tricky thing for the training part, as also like in your slides you have mentioned. So for the hyperparameters and the many different factors, they can also affect the training, right? And the training time and the conversion. So for the training part, so how can we like create kind of like a relatively fair playground for all the participants?
Yeah. So this is a case where certain hyperparameters are fixed, certain ones you can adjust. This is one of the next steps when we meet with the advisory board again, is going to get which ones do we think we should fix, and for those that are fixed, what should the fixed values be? But also when someone submits their numbers, they have to actually submit like all the hyperparameters that they use. And other vendors are allowed to look at these, and they can try to rerun their experiment using those hyperparameter settings to see if they can improve their own model. So the hyperparameter configurations are made available in advance. And like, let's say you do great only because of your hyperparameter settings. Everyone else is potentially free to like rerun using them, and they may see that same benefit.
And how about the optimizer? Because we know they have different optimizers. They may also play.
Yeah. So there's some flexibility there. So we, for example, using techniques like LAM and such. Some of the configurations that Google and NVIDIA use for the submitting training numbers can get quite large, and beyond a certain threshold, they need to use different optimizers. So again, you're allowed to use your preferred optimizer, but you have to make it clear what you were doing. So like all source code has to be submitted along with the submission.
And one last question. If no other audience want to ask a question, I have one last question. And actually, this is also kind of a bit tricky one. So we know that MLPerf that is try to play a evaluation platform for all the different type of the computing hardware solutions, right? And actually, in past years, we have heard the different opinions. About what is kind of the most suitable computing platform format for the autonomous driving. Some says it's kind of still GPU, some says it's maybe the FPGA, and someone said that maybe it's kind of the autonomous driving specific SoC. So since your research area is under like the computer architecture, so I was wondering, how about your opinion for that?
So I mean, I don't think there's a definitive answer yet. That's part of why we're doing this work. And particularly in the AV space, I think the architecture that you go with is driven by economics just as much as it is performance. So like it's been shown that GPUs still work very well for machine learning. The question is, do you want to continue paying NVIDIA prices for every vehicle that you sell? So that Tesla cited that as their primary motivation for why they built their own SoC. And some of the other players taking that same path have, I think, similar motivations.
So how do you think about the future of the FPGA in the AV?
So
because someone argues that FPGA is kind of configurable, and since you have like the very high kind of the dynamic workloads and the rapid developing the algorithms.
So I think I know there are companies looking at this. So AMD has expressed interest in putting Xilinx FPGAs in cars. I think I'm not aware of like large scale deployment of FPGAs to do self-driving so far, but it's certainly something people are looking at, and having representative benchmarks that they can run and submit their numbers on would go a long way towards helping answer that question.
Okay, thank you very much. So any other questions from the audience?
I wouldn't mind asking one more question.
Yes, go ahead.
You mentioned Tesla, and Tesla famously, I don't know truly, but famously says that they don't like LiDAR. I don't know if they're a partner with ML Commons, but how do you so you have chosen to benchmark a LiDAR plus camera methodology. How does Tesla deal with that? How do you benchmark their stuff against that, or how does that all come together?
Well, I mean, first of all, I think it's unlikely that Tesla would ever submit numbers for this, given that they're not selling their hardware.
I see. Yeah.
It's basically based on consensus. This is what people are currently doing. Some companies are free to disagree. Like Tesla's not the only company doing camera only ML.
Yeah.
And I mean, like Tesla is selling cars, they're not selling chips, so they likely have no interest in submitting to this anyway.
I see. Okay, that makes sense. Yeah. Thank you.
Okay. So let's thank our speaker again. Thank you very much, Tom. So you bring us a very interesting talk. And also thank everyone to attend our today's seminar talk. And our next talk will be the next Thursday, still 11 a.m. Eastern time. And thank you very much. Thank you, Tom. Have a wonderful day. Thank you. Have a wonderful day.
You too. Bye.
Bye.